Welcome back. So, in this video lecture, we are going to look at what is known as electrokinetic phenomena. So, under this umbrella called electrokinetic phenomena, there are several studies have been carried out by various scientists, right? So, one of them is very widely used, that is nothing but electrophoresis study. So, electrokinetic phenomena based on electrophoresis study is quite often used by colloidal scientists in determining the electrophoresis or electric mobility of the particle, charged particle. So, this is also helpful in determining zeta potential, right? We are going to look at why we measure zeta potential. We are going to address question on why we measure zeta potential, why not surface potential, right? So those things we will see in details in this video lecture. Let's begin. Yes, so as we described, there are several electrokinetic phenomena. Uh, let's say electrophoresis, electroosmosis, right? Sedimentation potential, steaming potential. So these four technique are being used under electrokinetic phenomena. What is what is widely used by colloidal scientists is the electrophoresis, right? So this is nothing but movement of particle, charged particle, okay, in an liquid electrolyte under the influence of electric field. That is nothing but electrophoresis study. Electroosmosis is quite different. Here the particle, charged particle will be stationary, whereas the liquid electrolyte will be a mobile phase, right, under the electric field. So this study is nothing but electroosmosis study. In various application, this study is used. For example, dewatering of soils for construction purposes, dewatering of waste sludges, etc. Sedimentation potential, steaming potential are the other electrokinetic phenomena. They are actually nothing but inverse of electrophoresis or inverse of electroosmosis. For example, in the case of sedimentation potential, uh, we are not applying electric potential, but electric potential is generated when charged particle is moving, right, forced to move under the relative to the stationary phase. Here stationary phase is nothing but electrolyte. On the other hand, steaming potential is nothing but study where generation of electric potential is uh, you know uh, is done by the movement of liquid electrolyte when solid being a stationary phase, right. This is also nothing but reverse electroosmosis. But here we will see electrophoresis and electroosmosis in a more detailed way. I have illustrated both electrophoresis and electroosmosis phenomena, right, as a schematics over here. You can see that electrophoresis is nothing but movement of the charged particle under the influence of electric field. Here these two electrode are important. So electric field, when electric field is applied, this will induce the movement of charged particle, but there will be electrolyte. So this particle will be surrounded by the electrolyte. Here electrolyte is stationary phase, charged particle is the mobile phase. On the other hand, electroosmosis, here the charged particle, I have not shown the electrical double layer here, but you can assume there is electrical double layer. So here the particle is stationary, whereas the liquid electrolyte is the mobile, right, mobile phase, right. So that is the difference between electrophoresis and the electroosmosis, right. Now why it is so important? Okay, how does this electrophoresis study movement of charged particle, okay, under the influence of electric field, okay, in the presence of electrolyte is important. That is exactly what we are going to look at in this slide. It is very important. We need to understand what is nothing but the Doppler shift, okay, how we can measure or determine the electrophoretic mobility, how this is useful in determining the zeta potential. That is exactly what we are looking at in this slide. So here if you look at, that whenever we introduce a charged object, right, into the electrolyte medium, So three kinds of counterions emerge, right? Strongly bound counterion, weakly bound counterion, and diffuse counterion. The strongly bound counterion and weakly bound counterion form the stem layer and shear layer, right? So the strongly bound counterion contribute to stern layer, whereas weakly bound counterion contribute to the shear layer, and the diffuse counterion contribute to the diffuse layer. So there are only three layers. Whenever you introduce the charged particle, the electrical double layer is developed. Okay, it consists of three layers: stern layer, shear layer, and diffuse layer, right? Now the stern layer and the shear layer is a rigid layer. Okay, that is something you must know, keep in mind. So the stern layer and the shear layer together form the rigid layer, whereas diffuse layer is kind of a porous layer. So when I say porous, meaning it can allow the light to pass through, but the rigid layer will not allow the light to pass through. Let us say if I shine a laser light onto the particle surface, you may be imagining that the light will strike the particle surface, but actually not. Fundamentally, they will not strike the particle surface, they will strike the outermost layer, that is the shear layer. That is why whenever you measure the potential, we do not call it as a surface potential, because the potential that we measure is at the boundary between shear and the diffuse layer. Okay. So this is because this is why we say that whatever we measure, potential that we measure is zeta potential, not the surface potential. Okay. Okay, so we know that there are three layers. So the stern layer and shear layer form the rigid layer, whereas diffuse layer is a porous layer that will allow the light to pass through. Now, what is known as Doppler effect is what is very useful for us to measure the electrophoretic mobility. So what happens is, whenever you shine a laser light, because the particle is under the movement continuously under the influence of electric field, because the laser light is now striking the surface of the particle when the particle is subject to movement under the electric field. So that actually create a shift in the frequency of laser light, right? That is nothing but Doppler shift. Okay. And because it creates a shift in the frequency, we can actually collect this information as a function of distance, and eventually this shift in the frequency as a result of the movement of the particle is actually a process to get details such as electrophoretic mobility. When I say electrophoretic mobility, it is not just the velocity, it is velocity per unit electric field. Okay, that is what exactly we measure. As we move on, you will be knowing how this electric field is useful for us to measure the zeta potential, right? Sorry, the electrophoretic mobility. No, you will be so you will be you will be able to understand that how this is useful in determining the zeta potential, which is the potential measured at the boundary between shear as well and the shear and the diffuse layer, right? Now you will be wondering to know that this Doppler technology is what actually being used in the Chandrayaan, the recent spacecraft that we sent to moon, right? In India's mission, the one of the successful, uh, you know, uh, the reasons for one of the reasons for the achieving the soft landing is because of the technology called Doppler shift. This is actually helpful in determining the spacecraft velocity as a function of distance, right? So that you will be able to track the speed at which the spacecraft is approaching the land, right? So with this, you will be able to control the speed of the spacecraft as well. So this is in fact housed in the spacecraft, right? Such that so that you that I mean because of that we were able to track the speed of the spacecraft velocity when it was approaching the moon land, right? Right. So this is very interesting technology, right? So this is what exactly we are going to look at. So next slide we will be looking at how we can get the fundamental equation, governing equation as a function of so we will be able to measure zeta potential by knowing the electrophoretic mobility. That is what exactly we are going to look at now. So we will start from here. So the governing equation for this problem is starting from the force balance. That is, there are two counteracting forces acting in this. One is whenever you suspend a charged particle, and when it is subject to the movement under the electric field in the presence of electrolyte medium, there will be two counteracting forces. One will be force due to electric field, because the particle is charged, there is electric field, so the particle is under the movement, okay, with respect to electric field. So there will be force experienced by the particle, that is due to electric field. That is nothing but Q into E. E is electric field, Q is charge. Now on the other hand, when particle is subject to movement under the electric field, there will be counteracting force, that is due to viscosity of the medium, right. So there will be viscous force in the opposite direction, right. If particle is moving in this direction, right, there will be counteracting forces in the opposite direction because of the viscosity of the medium, right. So you will have viscous force also coming out. So at equilibrium or stationary state, you can say that both these forces are equal, right. Okay, both these forces balance each other, right. So if I equate these two forces, I will get QE is nothing but QE is equal to 6 pi eta RSV, right. I know V by E, this is nothing but U, which is electrophoretic mobility. ZE is nothing but Q itself. So you have 6 pi eta RS, right. So this is a governing equation for this scenario. Now very interesting analogy we need to go through. Let us say we have got the steam line, or you can say potential line. Here if I suspend a charged particle having different particle size, okay. If I consider that there are two different particle size, okay, having different size, I mean particle with the different size, maybe K inverse is same in both these cases. In one case we say that KRS is very small, and the other case we say that KRS is very large. So KRS meaning K meaning inverse of K inverse, right. So when I say K is very small, K inverse is large. K is large meaning K inverse is small, right. So you should understand that, okay. And but in this case, because K inverse is kept constant, we are changing the radius of the particle. So we can say that the radius of the particle is very small in one case, radius of the particle is very larger in another case. So you can say KRS is small, KRS is large, right. If you see that when KRS is small, you see that this potential diagram is traversing in this moving moving past the charged particle, but the potential line is straight line throughout, right, as they move along the particle surface, right. There is no variation in the particle near the particle surface, right. Whereas here if you look at the potential, the potential is actually changing across the particle surface. There is deformation, right, whereas here there is no deformation in the case when KRS is small, but there is a deformation when KRS is large, right. So which means that when you consider this condition, that is KRS is very small, you can say that zeta potential is same as the surface potential, because there is no variation in the potential across the surface. Which means what it comes to say is that when KRS is small, meaning your electrical double layer is very thick, right, which means that shear layer coincides with the surface itself. So you don't need to really worry about what is surface potential, what is zeta potential, what is stern potential, all are equal. Whereas in this case KRS is very large, meaning your surface potential is different, stern potential is different, zeta is different. So one has to really work out, okay, to find out what is the zeta in this case, whereas here your psi is same as zeta. So that is the understanding that we should have. Okay, so with this analogy, we can now look at the problem. Let's say we are talking about the spherical particle, charged particle. So let's say we use this spherical coordinate, okay, for this case, and we assume the one dimensional problem is valid. Okay, here if you solve this governing equation, you get this solution, right? Simply nothing but q by 4 pi e. E here is E naught ER and exponential minus kr, right? Okay. Remember similar equation we obtained for when we dealt with the even the planar surface, right? Yeah, yeah. I mean the Poisson equation, Laplace. I mean the Poisson-Boltzmann equation when we dealt with similar solution we obtained, right? So here we consider the spherical coordinate, but one dimensional problem. This is the equation that we obtained. Now, when we assume this condition, that is K inverse is very large, which means that thick elliptical double layer, there the zeta is same as the surface potential, we can say, right? Whereas in the case of, so if you just simply substitute this psi with zeta, okay, which means because psi is same as zeta, right? So if you simply substitute zeta with the psi, then the same equation can be used, right, as zeta equation, right? That is the idea. So if you use the same equation, now we know this exponential kr, because we assume k is very small, we can expand this exponential. So what you will get is 1 plus x square and so on. If you ignore the higher order term, you will get 1 plus kr itself. Remember, we said kr is very, very small, right? So in such case, you can get rid of this 1 by 1 plus kr term. You will be having this compact equation, that is q by 4 pi er. Okay, right. Now we know what is q. Q is nothing but Ze. Now if I substitute Ze from here, I will get u 6 pi eta rs, right? That is exactly what I will get. Now in this, if I cancels the pi and pi, denominator and numerator, you have 2 by 3, right? So when you say u is equal to 2 by 3 epsilon zeta by eta, epsilon is E naught into Er, right? So this is the equation you get. This is nothing but Huckel equation. Remember, this equation is valid only when kr is less than 0.1, because we assumed that kr is small and we expanded this exponential term, and then we got this compact equation. So which means that we have to pay for it. So that how we pay for it, we because we assume, I mean the constraint comes from this one, that is kr is less than 0.1, only you can use this equation. So that is the idea, right? Now the question comes, what if the kr is very large? Okay, for that one has to use this Helmholtz-Smoluchowski equation, which is also a compact equation. Instead of 2 by 3, one would get simply 1, right? The detailed derivation can be obtained from this textbook. Okay, you can refer to this book for the for more clarity. Now this is the case when thin elliptical double layer is assumed. Okay, in that case this 2 by 3 factor is not coming. So 2 by 3 factor vanishes, so you will only have 1. Okay, so you can also write this equation because this is valid for kr greater than 100. You can write in one case you have equation less than 0.1, in another case you have equation greater than 100. So one can also write simply nothing but write this equation simply as c into epsilon zeta by eta. So c is 1 when Smoluchowski is considered, and c is 2 by 3 when Huckel equation is considered, right? So this is how one has to use this equation, right? Yeah. Now the question comes, what if the KRS is in between, right? So that is the important questions to be addressed. Now in this, you know that when KRS is 0.1, you have the equation, less than 0.1 we have the equation, when Kr is greater than 100, we have Helmholtz-Smoluchowski equation, right, uh, to determine zeta. Okay. So, basically what we do is we determine electrophoretic mobility from the zeta sizer. Basically, fundamentally it measures electrophoretic mobility and then it substitutes in the equation, and then finally you get the zeta potential. So, that is how you measure zeta potential. And now question is, what if the value is in between? Let us say it is between 0.1 to 100. That is addressed by what is known as Henry's equation. If you look at the Henry's equation, this equation additionally uses f of alpha term here, and for KRS less than 1, f of alpha is different, and for KRS greater than 1, you have to use different f of alpha equation, and if you substitute this over here, you will be able to generate a plot like this. Okay. Now, you have several scenario now. What if it is low potential, that is less than 25 millivolt? This plot, you will be getting a simple plot something like this at low potential for for various potential, that is greater than 25 millivolt. Okay, zeta potential greater than 25 millivolt, you will be getting different plot something like this, and at different KRS, right. So, one needs to understand at different KRS what is going to be my C, because in the equation what is known is what is not known is C, because you know this, right, E zeta by eta, we do not know what is C. Okay, it can be between 0.1 to 100. For that, you need to generate this plot and understand what is C. For let us say, if you are somewhere in here 1, if when KRS is 1 or when KR is 10, what is my C corresponding to the zeta potential value that we are referring to. So, that is how you will be able to get the value for C, right. Okay. So, here what we need to also know is let us say above 100, this equation is converging towards the Smoluchowski, Helmholtz-Smoluchowski equation, because beyond 100 the C is 1. Similar way, less than 0.1 it is also converging to that of the Huckel equation. So, below 0.1 and greater than 100, Henry's equation also yields value similar to Smoluchowski and Huckel equation. So, in between you can safely use any value by knowing what is KRS, by knowing what is zeta potential. That is the idea of using Henry's equation. Now, the question is, whenever you use the zeta sizer, what one needs to do is, first thing that you should do is calculate what is screening Debye screening length, that is K inverse. Okay, and then you know what is the radius of the particle that you are dealing with. Okay. So, now you can know that inverse of K inverse is nothing but K. So, you will be getting K into Rs. So, KRS, the product of KRS will yield one value. If it is less than 0.1, let us say, then in the software, when you do experiment with the zeta sizer, in the software you will have 3 different model listed out. So, when less than 0.1 comes, you should choose Huckel equation, Huckel model. Okay. When it is greater than 100, you should choose Helmholtz-Smoluchowski model. Okay. If it is in between, you have to choose Henry's model. So, this is how you have to do your experiment. Okay. And you cannot do any experiment randomly without knowing these details, right. So, and I am sure you will be able to appreciate this concept behind this electrokinetic phenomena. So far whatever we have come across, what we need to understand is, whenever you introduce a charged surface into the electrolyte medium, there will be 3 kinds of counterions emerging: strongly bound, weakly bound, and diffuse counterion. Okay. The strongly bound, weakly bound contributes to Stern layer, shear layer, and the diffuse counterion contribute to diffuse layer. Diffuse layer is porous layer, which means it will allow the light to pass through, whereas the the stern layer and shear layer are strong and rigid layer that will not allow any light to pass through. So, whenever you shine a laser light, it is not striking the particle surface. Remember that this is very important concept. It is striking the outermost layer, that is nothing but your shear layer. So, whatever potential you measure is the potential at the boundary between shear and diffuse layer. Okay, it is not the surface potential, right? So, this concept you must know. So, because we are not measuring the surface potential, we are using this analogy called KRS is small, KRS is large. When KRS is small, you are still allowed to, we can safely use the surface potential equation as a zeta potential equation by substituting surface as zeta potential, right. When KRS is large, then the problem comes. So, for that there is a detailed derivation by shown by Helmholtz Smoluchowski. So, one has to go through this textbook, okay. There it is given in details. So, the final and compact equation in that case will be, that is also same as the zeta potential, but your C factor will be different there. It is 1 instead of 2 by 3, right. So, once you know that, so you know in one hand you have Huckel equation because it comes from the approximation, okay. Other hand you have Smoluchowski equation, okay. And although we have not shown the detailed derivation here, you can very well you can go through the textbook. The other one is the Henry equation, that is in between, right. So, these things should be very clear, and this electrokinetic phenomena is very interesting topic, and people often use this electrophoresis study nowadays to do many problem solving, okay. And I hope these things are very clear now. We will stop here. We will continue from the next lecture. Thank you.